Yeah, I think now. So quick look in the question. This question. Quick look. So water is pumped from a reservoir and discharged into the atmosphere. This one is atmosphere. Okay. The inlet pipe from the reservoir to the pump has length L1. This one is L1. Is 1,000 meter, and the diameter D1 is 0.22 meter. Okay. On the discharge side, the length L2 is 500 meter. 500 meter. This question is a question in the tutorial 8. This one in tutorial 8. Okay, 8 tutorial 8. And this one is a question in the final exam. Let me see, 3 years ago. 3 years ago. The question in the final exam 3 years ago. Okay. And the pipe length L2 here and D2 0.18 meter. Both pipes are of clean cast iron, the material. Okay. Clean cast iron, it means we from this one, based on this one, we will have roundness. The roundness of cast iron is 0.26 millimeter. Okay, it means we have epsilon 0.26 millimeter. Clean cast iron. S is 5 meter. Okay, find the water flow rate and pump power when the cavitation is about to begin at the pump inlet. Water temperature is 20 Celsius and system is at sea level. Okay, this one is what we did yesterday. And here, yesterday, to find flow rate, we have to know velocity. Okay, and to know velocity, we have to use energy equation or Bernoulli equation. Okay, and in here we have point A, point B, point C, and point D. With point A, water surface, we have we know 3 things: pressure, velocity, and Z. Point B, we have Z is 5 meter, and because cavitation is a pump inlet, so we know pressure. PB is 2.34 kPa. Okay, so B we know 2 things. Point C we only know Z, and point D we know 2 things is Z and pressure, because PB, so PD equal to atmospheric pressure 101.3 kPa. Okay, so to find Q volume flow rate, we have to choose 2 points to write energy equation. Okay, and it's similar to the question 2 today. To find Q, you choose 2 points, and between 2 points you don't have anything. Okay, don't have anything. It means you don't have S pump, no S pump, no S turbine, no added energy, no extracted energy. Okay, so in this case, you can choose point A and point B, or point C and point D, because between A and B or C and D, we don't have pump. Okay, but A and B is our choice yesterday, because A we know everything, and B we know pressure and Z. Okay, C just only 1, and D 2. So A and B is our choice yesterday. A and B. Okay, so we have energy equation. PA over rho Z, VA over 2Z, that's A, equal to PB over rho Z, VB square over 2Z, and that's B. And SL, energy loss, because now we have real flow, not ideal flow. If ideal flow, SL is 0. So when SL is 0, that's easy, very easy to find VB, because everything we have: pressure, PA, VA, ZA, PV just B we have. So if SL is 0, easy. But now SL not 0. It's real flow. Okay. So SL equal to major energy loss plus minor energy loss. Major and minor energy loss. And because in the question you can give some assumption. When you can give some assumption, you can assume a minor loss is 0. Because actually the minor loss is very small compared with major loss. Okay. So if in the question it's not mentioned to minor loss, you can ignore minor loss. Okay. So in this question, if we ignore minor loss, SL will be equal to major loss, and major loss is friction loss. Friction loss will be equal to friction coefficient F L over D V square over 2G. It means SL depends on velocity VB, and F depends on F from Moody diagram. You have F from Moody diagram. F will based on epsilon over D and Reynolds number. Okay, and inside Reynolds number you have VB. You have VB. Okay, so in this case, as I said yesterday, we have to use try and errors methods. Try and errors. Try and errors. Okay, try and errors. Because F you can't find, you see, you can't find VB without SL. You don't know SL, you can't find VB. But from equation 2, you can't find SL if you don't know velocity. It's messy. Okay, you have to know VB. You have to know SL to find VB, but to find SL you have to know VB. Okay, so in this case you have to try and error method. Try and error methods is mean you can assume you have VB. For example, you have VB. You can assume you have VB or F. It's up to you. Okay, but if I assume F, I have VB is 1 meter per second. Okay, you can give one number. You can give 2 meters per second, 10 meters per second. It's up to you. Okay, and if you assume I have VB is 1 meter per second. Okay, what have VB? We can find Reynolds number. Reynolds number. I call this one is equation 3. This one is Reynolds number is equation 4. Okay, Reynolds number from equation 4. Okay, and epsilon over D. Epsilon is 0.26 millimeter. D is inside diameter is 220 millimeter. So based on epsilon over D and Reynolds number and Moody diagram, you can find F. Okay, Moody diagram is this one. Okay, this one. Epsilon over D and Reynolds number, you can find F. F. When you have F based on equation 3, you can find SL. Equation 2, you can find SL. And when you have SL based on equation 1, now we have SL, you can find VB. Okay, and VB will be is input of the next loop. Okay, and you try again until VB2 at the end minus VB1 divided by VB1 times 100 is smaller or equal to 5%. The difference between VB at the beginning and the end of the slope is smaller than 5%. It's okay. In this question, if just only in this question, if we assume VB is 1 meter per second, I'm very lucky because VB2, if you assume VB1, if you assume VB1 is 1 meter per second, you can find VB2 is, let me see, is VB2 is 1.04. Okay, it means now it's VB2 minus VB1 divided by VB1 times 100 smaller than 5%. It means just only one term I have the results. One term I have the result because my assumption is very close with the results. But if I assume VB1 is 10 bits per second, maybe I have to do this one 5 or 10 times to have the result. Okay, 5 or 10 times is so if you see this question, it's up. You have to if the first assumption you see the difference between VB1 and VB2 is too far, you have to choose VB again. Do it again. Maybe it make it smaller, much more smaller, or much bigger. Okay. So it depends on your lucky. You can do it 1 time, 2 times, or 5 or 10 times. Okay. So for example, in this question, if we assume VB is 1, VB2 is 1.04, it's very lucky. It's good. So just say only one time you have the results VB is 1 meter per second. And when we have VB 1 meter per second, Q will be equal to VB times AB. So you have the results. Okay. But if you choose 10 meters per second, maybe you have to do it 5 times to have the results is 1 meter per second. Okay. You got it? Do you know how to do this question? How to do this question? Do you have any question about how to find VB in real flow? This one is real flow. Okay, thank you. So you will have Q is around 0.03 s meter square meter cube per second. This is the first question. Okay. The second one asks you for P pump. Okay, it's similar to our question today. You have to find P pump. So to find P pump, you have to find S pump. Okay, to find S pump, energy equation. And you have to choose 2 points. Which point you choose in this case to find P pump? We have A, B, C, and D. Which point you choose? Which points? A and D, yeah. A and D. A and D. Okay. So A and D, energy equation. PA over rho Z, VA square over 2Z, that's A, equal to PB over rho Z, BB square over 2Z, that's B, and energy loss. Energy loss. Okay, the problem is at the energy loss. With PA, we use 101.3 or 101.3 kPa. It's 101.01300 Pascal. VA is 0 and ZA is 0. Oh, sorry, point D, not point B, sorry. Point D. D. Okay. Oh yeah, I forgot 8 pump. Between A and D, we have pump. So 8 pump. Okay, S pump. PD atmospheric pressure 101,300 Pascal. VD how about VD? How about VD? Velocity. How about VD? How about VD? How about velocity? VD. In the question one, we know volume flow rate already. Now, to answer, we have volume flow rate already. So when you see V, you have to think about volume flow rate. Q divided by AD. Q we have from the question one here. ZD is 5 meter. 5 meter. Okay. So now is SL, energy loss. SL equal to S major and S minor. S minor is similar to question one. We assume as 0. So S major energy loss or friction loss. But in here we have two pies. The big pies before the pump and small pies after the pump. So with a different diameter, we have the different friction loss. Okay, you see, we have the different in the experiment A, part A of the experiment of the lab one. Okay, we have the different pipe diameter, the small pie and the big pie. With small pie and big pie, the friction coefficient and the friction loss are different. Okay, so in this case, S major will be is friction coefficient SF as a big pie. I call it pi 1 and SF as pi 2. With pi 1 and pi 2, pi 1 is this one and pi 2 is after the pump. Okay, so SF1 plus SF2. With SF1 equation, friction coefficient F L1 over D1, the big pipe before the pump, V1 square over 2Z. Okay. With V1 is velocity in the big pie, and the big pie, the diameter is constant. The diameter is constant, volume flow rate constant, so velocity constant. So V1 will be equal to VB, or yeah, VB. V1 equal to VB, or 1 meter per second. Okay, L1 we have is 1000 meter. D1 is 0.22 meter. Is 0.22 meter. And F1 friction coefficient depends on epsilon over D1. With epsilon is let me see, point F1 0.26 millimeter divided by 220 millimeter. 220 millimeter is the diameter of pi 1. Okay, pi 1. And Reynolds number 1. Reynolds number 1 equal to rho VD, rho 1, V1, D1 divided by mu1. Okay. With rho 1, 1000. V1 is VB1 meter per second. D1 0.22 meter. And mu1 from viscosity of water. Water, for example, water at 20 Celsius, we have viscosity, yeah, at 20 Celsius is 1.002 times minus 3. Okay. It's 1.002 times minus 3. So from here, you have Reynolds number. Okay. From Reynolds number and epsilon over D, you find F1 from Moody diagram. In this question, in question 2, you don't have to use triangle methods, because in question 2, we know velocity already. Okay. When we know velocity, we can find friction coefficient from Moody diagram. Okay. So F1 you can find directly from Moody diagram. It's similar to SF1. It's SF2 to F2 L2 over D2 V2 square over 2Z. Okay. With V2, this one is VD. V2 is small pipe, or V2 equal to VD. Okay. With VD, you have here Q divided by cross-section area. L2, 500 meter. D2, we have is 0.18 meter is given. And F2 is similar from epsilon over D2 and Reynolds number 2. Okay. With epsilon over D2 is 0.26 divided by 180 millimeter. 0.26 millimeter is the roundness. Okay. With Reynolds number 2 equal to rho 2 V2 D2 divided by mu2. In this equation, just only is V2 is different equal to VD, and D2 is 0.18 meter. Okay, and the density constant 1000. Mu2 is constant 1.002 times 10 minus 3 because the temperature is constant. Okay, so from this one, you find F2 from Moody. Okay, so from Moody diagram, you find F2. From Moody diagram, you find F1. Okay, from F1, you have find SF1. From F2, you find SF2. From SF2 and FF1, you find SL. Okay, and from SL, you find S pump. From S pump, you find P pump. Okay, got it? The step by step from V1 equal to VB, you find Reynolds number 1. From Reynolds number 1 and epsilon over D1, you find friction coefficient F1. Friction coefficient F1, you find SF1. Okay, from V2 equal to VD, you find Reynolds number 2. From Reynolds number 2 and epsilon over D2, you find F2. This one is from Moody. Okay. From F2, you find SF2. From SF1 and SF2, you find SL. Okay. From SL, you find S pump. And from S pump, you find P pump. step by step. Okay. And the result you have on UTS Online. I show you the process. Okay, how to get the P pump.